Hello everyone, welcome to the video. In this video, I am going to discuss about an important topic, composition of function and inverse of a function. That is how to compose two functions and how to obtain the inverse of a function. The theory part will be discussed in this video. I recommend you to watch two videos that I have already uploaded in my channel about the types of function and related problems of the types of function. So before watching this video, you are requested to watch that two videos in my channel. Here I will also give you the link of the two videos. So let's get into the video. So here I will first discuss about composition of function, and then I will go through the inverse of function, and then there are some related theorems about the composition of function and inverse of function. So I will discuss that topic later on. So these are the topics to be discussed in this class or in this video. So the first topic I am going to discuss about composition of function. You see, so first you see the definition of composition of function. We have three sets A, B and C. These are three non-empty sets. The set should be non-empty because on empty set you cannot define function. Okay, so there are three sets A, B and C, non-empty sets, and we have two functions. The first function f is from A to B and the second function is z from B to C. These are the two functions. It is important thing. First function codomain is B and second function domain is B. This should be common. Okay, so you have two functions. Now you can compose these two functions. So then the composition of f and z is denoted by this symbol. It is again important. Composition GOF, that means f is the first function and z is the second function. You have to write in reverse order. Okay, so and it is defined as GOF. This is the function from A to C. You see, GOF, this function is from A to C. That means from A bypassing the set B to C. So GOF, this is a single function. Now you see, GOF, this function is from A to C. You have to bypass the set B, and it's defined on all elements of the domain of GOF, and domain of GOF is A. So we are to write for all x belongs to A. So image of x under the function GOF will be is equal to image of z, this function z, image of fx, not z, image of fx under the function z. So this is the definition of GOF. You see one note here. So first, since f is a function from A to B, it is clear. Therefore, since f is a function from A to B, therefore for all the elements in A, there is an unique element. There is a unique element in B. There exists unique element in B. For x, the element is fx. So there exists a unique element fx in B, and again z is a function from B to C. So therefore the pre-image under the function z is fx now. So again, since z is a function from B to C, therefore corresponding to each fx in B, because fx is the element in B, x is in A, so fx will be in B, and then fx has the image in C, and that will be g of fx, that is g of the element in B, that is fx. So g of fx, this element will be in C. You see the you see a oval diagram, an oval diagram. It will be clear to you. So you see the oval diagram. That is, we have already considered in the previous screen that f is a function from A to B and z is a function from B to C. So this was the supposition to get a composition of functions. Okay, so you have two functions, first function from A to B and the second one from B to C. Then as per definition of the composition of function, that GOF means this function GOF, it will be from A to C. Just you have to bypass the set B, intermediate set B, then it will be from A to C. This is the new function, and the domain of new function is again A and codomain is C. Now you see, when you have considered the function f from A to B, then for all elements x in A, there must be unique element y in B such that y is the image of x under the function f, and that is written as fx. Okay, so image of x under f is fx, that is represented by y. Now come to the function g function. This function from B to C, and this time for all y in B, there is the image of y under z will be zy. Image of y under the function z will be gy, that is gy is an element of the set C, and that is generally denoted by z. And g of y is actually what? Y is actually fx. This is the composition g fx, and this is now the image of x under the function gof. This g of fx means gof of x. I have already written in the previous screen that the image of x under gof will be gof of x, as like fx is the image of x, zy is the image of y. So gof x is the image of x under gof, and that is actually g of fx. You got my point. Now one important thing is that for the set B, you see, for the set B, when you are finding the image of all elements in A in the set B, if this f function is not onto, you think deeply, if the function f is not onto, then in the set B there are some elements which are not the image of the elements of the set A. Okay, so that means there will be some free elements here. And we know the range of a function is the subset of the codomain. Range means the set of images, and codomain means the whole set. Okay, so range of any function is a subset of the codomain of the function. So that means here also the range is the subset of B, and B is what actually? B is the domain of Z. So to get the function gof, if you want to find the function gof, then the range of the function f, this function f, range of the function f mean some elements of B or all elements of B, is a subset of the codomain of Z. This is the main condition to get the composition of two functions. Range of the first function, that is f, should be subset of the domain of the second function, means Z. So range is subset of the codomain of Z. Range of f subset codomain of Z. Then you can find gof. Gof should be written in reverse order. F, though we have written gof, actually f is the first function, Z is the second one. Okay, so to get the composition gof, we must have the range of f is a subset of the domain of G. You should memorize this one, you should understand this one. And now you see one note here. Already I told you that the domain of gof is same as the domain of f. You see the figure, oval diagram. GOF domain was A, and the domain of f is also A. And here you see the composition GOF. This is exist when and only when the domain range of f is the subset of domain of Z. So if the range of f is a subset of the domain of Z. This is the condition to get the composition of GOF. Okay, so you see the next part. Similarly, if you want to find the composition f of z, if you want to find the composition f of z means this time z is the first function, f is the second function. F of z is first, f is second. So to obtain the composition f of z, then this time the range of z must be subset of the domain of f. So we have written here that exists if the range of z, this one, is a subset of the domain of f, this one. Okay, so you see here, if both the functions f of z and g of f, these are exist, so in that case, in general, these two are actually unequal. F of z and g of f both are exist mean range of f is a subset of domain of g, as well range of z is a subset of domain of f. So in that case, f of z and g of f both are exist. So if both the functions f of z, g of f are exist, then generally g of f and f of z, they are unequal in general. But if it is identity function, say f is I, g o I, in that case g o I equal to I of z. But if the functions are not identity function, in that case these two cannot be equal. In general, they are not equal. In some special cases it may be equal, but the speciality is the function, one of the functions should be identity function. Okay, so next you see one example about this. See the example. Suppose we have the function f is from R to R, and definition is fx equal to x square, and similarly g is a function from again R to R, and gx definition is 2x plus 1. Then actually composition of function is what? Composition of function mean function of function, function within function. That is called composition of function. Is that clear? So whenever you want to find the function f of z, that is the composition f of z, then if you eliminate this o, this is actually what? F of zx. This is f of zx. When you do not write this o, then gx will be the input of the function f. Okay, so this o is eliminated, then f gx, and that is equal to, see the function f, the outer function is f, so function fx is equal to x square. Fx is equal to x square, that is whatever you are writing inside f, that on the right side it is square of that number x, so then it is x square, and this time it is f of gx, mean f inside is gx, therefore this is also gx square. So whatever you are writing inside f, here we are writing inside f as gx, this is the input, so this x should be replaced by gx, square is here. And now go to the function z function is given here, g of x, then it is twice x plus 1, so we just replace gx is equal to 2x plus 1 and whole square is this. So this is your f of z, this is f of z. Then try to find g of f. So g of f of x, o is eliminated, then g input will be fx. Now go to the function z, outer function z, so g of x, then it is 2x plus 1, so this time this x is replaced by, you see here, this x is replaced by what? Fx. X is replaced by fx, so therefore gx is equal to 2x plus 1, so this time 2fx plus 1, and what is fx? Fx is x square, you see here, x square. Okay, I think it is clear to you. Okay, so then you see that fx is g of f is equal to 2x square plus 1, and f of z is equal to twice x plus 1 whole square, and these are actually unequal functions, and therefore f of z not equal to g of f. Okay, okay, see the next topic. We have a theorem. The theorem is, if f a to b and z b to c both are 1 functions, and already we know what is 1 function, so both are 1 function, then GOF, that is composition of z and f, this a to c is also 1. So if you want to write in only one sentence, then you can write like this: the composition of two 1 functions is again a 1 function. That is the main topic actually. Composition of two 1 function is again 1 function. So let me prove this theorem. So first of all, to check whether a function is 1 or not, we are to take two elements in the domain of the function. So the x1 and x2, these are the two elements in the domain of the function g of f. G of f function domain is a. So we are writing a in the set a. You see which function you are going to show. The function you are going to show 1 you are to take two elements from the domain of that function. So we are taking x1 and x2 from the domain of g of f function, because our target is to show that g of f is 1 and so we are taking x1 x2 in the domain of g of f, mean a. So we are taking a such that the condition was what? Such that in general we write fx1 is equal to fx2, but here the function is not f, here the function is g of f. Here the function is g of f, this function. So we write g of f of x, g of f of x1 equal to g of f of x2. So you see that one, g of f x1 is equal to g of f x2. Okay, and you see if you eliminate this o, if you do not write this o, then g input will be fx1 and here z input will be fx2. So we write that one. So g of fx1 is equal to g of fx2. Now go to the definition of the function. You see this function g of z from b to c is 1 function. You see this is a 1 function. So what was the definition of 1 function? This is the definition. You see here fx1 equal to fx2. If you have these two functions fx2, in case of the function is 1 then these are the actually image. Then in case of 1 we should get x1 is equal to x2, is not it? X1 is equal to x2. That means this f is eliminated from both sides. So here you see the function z, this function z is 1 you see here both are 1 means z is also 1 therefore we should write fx1 is equal to fx2, that is the pre-images of z are also equal. So we write that one, fx1 equal to fx2, and the condition is since z is 1 under this argument gfx1 equal to gfx2 will give us fx1 is equal to fx2, that is pre-images of the function z are also equal because the function z is 1 and again you see f is also 1 f is also 1 and therefore the pre-images of the function f are also equal. That means x1 is equal to x2, this one x1 is equal to x2 because f is a 1 function. Is that clear? So you see another example. Let me erase this. Okay, let me take another theorem. This is a theorem again. If f a to b and z b to c, this time both are onto functions. In the previous theorem both are 1 function and this time both are onto functions, then g of f a to c, this is also onto. That means you can write in one sentence that the composition of two onto functions is again an onto function. Okay, so let me prove this one again. So how to check whether a function is onto or not? In this case we are to take some element, one element in the codomain of the function, and we are to check whether for that element in the codomain we have pre-image in the domain or not. If that element has the pre-image in the domain, then we say that the function is onto. And there is also another way to show a function is onto. The another way was to check the range and codomain. If range and codomain are codomains are equal, then we say that the functions are onto. But here you see the function is not given. What is fx and what is gx? So without fx is equal to or without gx is equal to, you cannot find the domain and range of the function. So in this case you are to take the first process, mean taking y in the codomain of the function GOF. Codomain of the function is C. So you are to take y in C, and you have to show that for that y in C or z in C, actually z element is taken in C. So for that z in C, you have x in A or not. That is your target. Okay, so let me prove this one. So first of all, you take, let Z be any arbitrary element of the set C. That means the codomain of GOF. So C. As Z is onto, because it is given in the statement of the theorem that Z and F both are onto functions. So Z is onto function. So since Z is onto, therefore C is the codomain of Z also. You see, C is the codomain of Z also, and Z is an onto function. So for the element Z in C, we have y in B in against of Z, because it is onto. So y must be in B such that Z equal to zy, is not it? So we have written here that so there exists an element y in B such that Z is equal to zy, because y is the pre-image of Z. Okay, so that means Z is the image of y under the function Z. So this is the condition that the function Z is onto. Again, you forget about the function Z. Now come to the function F, and for the function F, this time in the codomain of F, the element is y. This is y in B, so the element is y. And as F is also onto, therefore for that y we have an x in A such that y is equal to fx, is not it? So again, as F is onto, so there exists an element x in A such that y is equal to fx or fx is equal to y. Then you see, now we should go to the function GOF this time. Okay, so you see here GOF of x. This is GOF of x, that is image of x under GOF. We check whether image of x is z or not, and obviously that will be z. And if you write g, then the input of z function will be fx. So g of fx, then that is equal to g of fx is actually y. You see here fx is y, so gy, and y is actually z. Gy is actually z. Here gy is equal to z. So ultimately there is a relation between x and z under the function GOF, and this shows that the function is an onto function. You see. So therefore for all z in C there exists x in A such that GOFX is equal to z, such that GOF of x is equal to z, and so this function is an onto function. So GOF is onto. So this completes the proof of the theorem. Okay, so let me go to the next part. Is another theorem. Let f of A to B and g of B to C as well h of C to D. There are actually three functions, f A to B, then z B to C, then h C to D. You see here this function finished at B, z function begins at B, and z function finished at C, h function begins at C. That means FOZ, GOH, these are GOF, and HOZ, these are defined actually. So then the theorem is HOGOF will be equal to HOZOF, and this is the associative property of composition of functions. FOZ not equal to GOF. FOZ not equal to GOF, this is commutative property. That is, function composition of function does not satisfy the commutative property, commutativity, but it satisfies the associative property. This is associative property, just change of position of brackets. Okay, so to prove this one, you just take an element that is HOGOF. The domain of HOGOF is the domain of last function. Last function domain, f function domain is A, so total domain is also A. Okay, so you are to write x is in A. So x is in A, this one, for all x is in A. HOGOF of x will be is equal to h. this O is eliminated, so input will be 0 f of x. This is 0 f of x, and then h of 0 f of x, this O is eliminated. This time input of z is fx, so g of fx. No more, because you cannot proceed without the main definition, without the numeric definition of the functions f, z and h. So you should leave here and go with the right hand side, h o z o f. So that one, h o z o f. This time you eliminate this o, then input will be fx of hoz of fx. Okay, then again you eliminate this o. This time input of h will be z fx, and you see here this one and this one, they are equal. So therefore this is equal to this. So you write that one, HOZO f of x is equal to HOZO f of x, and then you can write these are the image of x under this total function are equal. So we can say that these functions are also equal. So we have written here HOZO f of x is equal HOZO f is equal to HOZO f. Okay. Now you see invertible function. This is most important topic of the chapter. Invertible function. Invertible means inverse of function. You see here the definition first. Let f is a function from a to b, and inverse of function is just the change of direction of function. Just the change of direction of function. F is a function from a to b, and inverse is a function of b to a. Inverse is a function, it is from b to a. Just the change of direction. So you should keep in mind this f inverse, it is actually not 1 by f. F inverse is not actually 1 by f. You should remind in your mind. F inverse, this f inverse, this is not equal to 1 by f. Actually this is not inverse, mean it is not index. F inverse, it is just denoting the inverse of a function. It is actually a new function, z type function. Z type function, z function. Okay, so f inverse is the change of direction of the function only. Okay, so this time you see for the function FOZ, for the function f from a to b, then we have another function f inverse from b to a. So when f inverse is a function, when f inverse is a function, and we know that this is a function for if for every element in B there must exist unique element in A. So we have written here which associates, that is f inverse associates each y of B. Y mean this time B is the domain now. So y of B to a unique element x of A mean codomain, such that f inverse of y, f inverse is a single function now. This is a simple function like z of b to a, like this. So z of y will be equal to x, mean x is the image of y under the function z, mean f inverse. So therefore if f is invertible, then y is equal to fx will imply f inverse y is equal to x. Very simple. So try to understand again. I am repeating this one. F is a function from a to b, this one. Then the inverse of f is a function from b to a. But one important thing is that this function, whenever you are going to find the inverse of a function, then the function must be 1, 1 and on 2. This is the main condition to get a function is invertible. Okay. So first of all you see this f inverse is a function from this function. F inverse is a function from b to a, just change of direction. As well, the function of which you are going to find the inverse must be 1, 1 and onto. If this function is not 1, 1 and onto, then inverse cannot be obtained and inverse does not exist. So this is the definition of the function. And you see the second definition, the invertible function can also be defined in another way also. This inverse of a function can also be defined as follows. You see, this f is a function from a to b, this is 1, 1 and onto function. Then the function z b to a, you see, already I told you that z is a function from b to a, this is reverse direction. This is reverse direction. This is 1 1 and 1 2, and z b to a, this is also 1 1 and 1 2, in such a way that f and z, these are two functions in such a way that GOF, mean the composition of f and z, this is equal to identity function. This a is written for the domain of GOF. The domain of GOF will be same as the domain of as the domain of f, and domain of f is a, so we have written here IA, and FOZ is equal to identity function I, and B is written for the domain of the function Z function domain is B, so IB. You see, if you have two functions like FA to B and ZB to A such that the composition is identity, composition of two functions is equal to identity function, then you can say that the functions are inverse of each other. Is that clear? As like in number theory, say 2 into inverse of 2 as multiplication. Inverse of 2 as multiplication is half, and identity element about multiplication is 1. So 2 into half is equal to 1. That means half is the inverse of 2 in case of number system. In the similar manner, the 1 in number system is similar as identity function in function. Okay, so if you have two functions f and z such that the composition is identity, then f is the inverse of z or z is the inverse of f. So GOF equal to IA, this a should be written as the domain of the last function, mean this one IA, and FOZ domain of this last function IB. Last mean actually first. FOZ, that is G then F, GOF, that is F then G. So where IA and IB are the identity functions on A and B respectively. Then this function Z is called the inverse of the function F, that is F inverse is equal to Z. Okay, let me go to the next part. We have a theorem again. F A to B and Z B to A, actually they are invertible functions, be two functions such that GOF is equal to IA, then F is 1 1 and Z is 1 2. F mean the first function is 1 1 and the second function must be on 2. Always this is a theorem. If you are finding GOF is equal to identity of function, identity on the set A, then the F function means first function is what? First function is 1 1, and the second function is what? Second function is on 2. Very simple proof, you see. So let x1 and x2, these are the elements of the set A. This A is the domain of F as well as GOF. So we are writing x1 x2 in A such that fx1 is equal to fx2. Okay, then you see g of fx1 and g of fx2, taking g on both sides because g is again a function. So for every element in B, these fx1 and fx2, these are actually elements of B. So every element in B has some image in the codomain of B, codomain of the z function z, that is A. So z can be taken on both sides, g of fx1, g of fx2. But g of fx1 is actually GOF of x1. You write that one, GOF x1, and this is GOF x2. Simple thing. But GOF is given as identity function I. So we can replace GOF by identity function. So identity of x1 is equal to identity of x2. And so identity function definition is Ix is equal to x. You know, it is given in the first year classes and also discussed in the previous videos of this chapter types of function. So Ia x1 will be equal to simply x1 and Ia x2 will be equal to simply x2. So x1 is equal to x2. So you see fx1 is equal to fx2. This was our supposition, and finally we got x1 is equal to x2, and that is why the function f is a 1 1 function. So we write that one, therefore f is 1 1. Now go to the second part. The second part is to show that z is onto. The function z is onto. So this time you are to take an element in the codomain of z. Codomain of z is A actually. So you are to take some elements in the codomain of z and to check whether for that element you have pre-image or not. You see that? So we have the function z of b to a. This is the function now. Now codomain is a. So in order to prove that z is onto, it is sufficient to prove that every element x in the codomain a, that is x in a, it has pre-image in b. B means the domain of the function z. So let x is an arbitrary element of the set a. Then f of a to b is a function. It is already given in the statement of the theorem. Then as f of a to b is a function. So since this is a function, therefore under the function f, the element x in a must have image y in b. So therefore fx is in b, and that is taken as y. This is y. So then f of x is equal to y, and that is implies g of, taking z on both sides, actually z of fx is equal to z of y. But z of fx is actually what? Z of fx is equal to GOF of x. So we write that GOF of x is equal to gy. But GOF is again identity element. So we write IA, identity function, not element, identity function, IA of x equal to gy. But IA of x, image will be x again because it is identity. So we write this is x, actually this is x, IA of x is equal to x, and gy is remaining same. So gy is equal to x. That means for all x in b, for all x in a, we have zy in b. So thus for every x in a, there exists y in b such that zy equal to x, and therefore f is an onto function. I think this is clear to you. Go to the next part. Again a theorem. F of a to b and z of b to a, these are two functions such that f of z is equal to identity of b, then z is onto, same thing, this is 1 and this is onto, as like the previous theorem you can prove this one actually. Okay, so I leave this one for you. You see a note here, the above two theorems shows that f a to b is invertible, this function is invertible if and only if it is a bisection, mean f is 1 as well as onto. Okay, then the function is invertible. This is one important thing. Okay, come to next topic. Again a theorem, f a to b and z b to c, these are two invertible functions, both are invertible. The inverse of f is f and inverse of z, both are exist, two invertible functions. Then GOF, that is composition of two invertible functions, is again invertible, and the inverse of GOF is equal to f inverse o z inverse. This is in the reverse order, f inverse z inverse, f inverse z inverse. Whole inverse, if you broken down this one, you have to write in the reverse order, f inverse o z inverse, like this. Okay, so try to prove this one. Since f and z are invertible functions, this is given in the statement of the theorem, f and z, these are invertible functions, therefore the composition of the function f and its inverse will be identity. Similarly, the composition of z and its inverse will be again identity because these are invertible functions. So we write that one. So f inverse of is identity, but what is the suffix? Suffix will be the domain of f. F domain is a, so IA. F inverse, this will be identity, but what is the domain of f inverse? F inverse domain will be, the direction is opposite, so domain will be b, so IB. Then G inverse OZ, the domain it is identity, but suffix will be b because domain of z is b, so b. And GOZ inverse will be equal to again identity, but the suffix of I will be c as the domain of z inverse. Z is this one, so inverse will be from c to b, so domain is c, IC. So this will be the consequence of the statement if f and z both are invertible functions. These are the consequence of this statement. Okay, now you are to show the function GOF is also invertible, and to show that this is equal to this. So you write that one. To prove that GOF is invertible, to check to prove this one is invertible and this is equal to this, mean the inverse of GOF is equal to f inverse OZ inverse, it is sufficient to prove that this is, consider this total function as a single function and this total function as a single function, and composition of this function and this function, you see here, consider this as single function, okay, this as single function total, and this as single function, say this is h and this is say r, like this. So it is sufficient to prove that, to prove this is equal to this, to prove this is equal to this, it is sufficient to prove that the composition of the total function, this one and this one, is equal to the identity function I. And what is the suffix? Suffix will be the domain of the last function. Domain of the last function is, this is the last function f, and domain of f is a. You know that one. You already written in the previous screen. So this is IA. And in the similar manner, either you are to prove this is equal to IA or GOF. This is GOF and this is F inverse OG inverse. Consider again, this is a single function, this is a single function. So composition of this function and this function is equal to identity. And suffix C, C is the domain of the last function G inverse. Okay, so either you prove this and this. Take one of these two. Okay, let me erase this one first. Okay, you see the proof. Now F inverse OG, I am taking this one, F inverse OG inverse whole operation GOF, and already we know that the composition of function, this is associative. That means we can change the position of brackets as per requirement. Okay, so we take this one, F inverse, order is same, you see, F inverse G inverse, then G. This order is same, just taking bracket with this, and OF is remaining same. Then this is again written as composition of function. So this bracket can be taken with G inverse and G like this. But G inverse OG, you have already seen in the previous screen, G inverse OG, this is identity function and the suffix is B. So we write that one. F inverse remaining same, this is identity with suffix B, and OF is remaining same. But F inverse and identity function composition will be the function itself, that is F inverse itself. So F inverse, this F is remaining same, then F inverse OF, this is already seen in the previous screen that it is again identity function, and suffix will be the domain of the function F is A. So our target is fulfilled, that this is equal to identity function in the set A. Okay, similarly you can show this one, need not to write in your exam, just you write similarly we can show that this is equal to this. So you write that similarly we can show that this is equal to this, and therefore the inverse of this function will be equal to this function, because the composition equal to identity, therefore one function is the inverse of the other function. So therefore GOF whole inverse will be equal to F inverse OG inverse. So that is the completion of the theorem. Again you take another theorem. If f is a function from a to b, this is invertible function, then its inverse will be unique. That means for a function there must not exist more than one inverse for the function. Okay, so first you take if it is possible, take there are two inverses for the function f. So we take, if possible, let g1 b to a. G1 is the inverse of f, so it will be change of direction, b to a. G1 b to a and g2 b to a, these are the two inverses of the function f a to b. If possible we are taking this, but actually it is not possible. Okay, so then since g1 is the inverse of f, therefore g1 and f composition will be identity. G2 and f composition will also be identity, because they are inverses of f, therefore composition will be equal to the identity function. This b is written for the codomain of the last function g1. G1 codomain is b, so I of b, and g2 codomain is also g2 domain, not codomain, g2 domain is b, and therefore it is b, ib. So then take y is an element in the domain of the function f of g1 and f of g2. So y belongs to b. Then for the first one, f of g1 of y will be equal to, this is identity function, this is given identity of y, and identity function image is the element itself. ib of y will be equal to y. In case of this part, it will also be like this, because f of g2, this is also I, so I y, and again this is an identity function, and therefore the image will be y itself. Okay, so then this one, and this one, both the right hand sides are equal, therefore the left hand side must also be equal. You write that one. So f o z1 of y is equal to f o z2 of y, and so eliminating that y, so f of z1y and f of z2y. As well, it is given in the statement of the theorem that f is an invertible function, and as f is an invertible function, therefore f is 1 1 as well as on 2. And from here, since f is 1 1, therefore this f can be eliminated, that is z1y is equal to z2y. You write that z1y will be equal to z2y. And so images of y under the function z1 and under the function z2 are equal, mean the function z1 and z2 are equal. So z1 and z2 are equal, and our consideration was wrong. We already considered that z1 and z2, these are inverses of f, but here we see that z1 and z2 are actually equal, and therefore their inverses are unique, inverse is unique. So thus the inverse of the function f is unique. Okay, so this is the proof. Come to the next part. So this is your theorem. If f x to y is invertible, then f double inverse is equal to f. Okay, so very simple proof. You see, since f x to y is invertible function, therefore f inverse is a function from y to x, like this, and so f inverse of inverse is again a function from x to y, this one. And so f inverse of, since f is inverse of f, therefore it is identity, and f o f inverse, these are inverse of each other, therefore it is also identity. And we are to show that this inverse of f double inverse and f inverse, f double inverse and f inverse is equal to identity function. Okay, so you are to write that one, f double inverse o f inverse is equal to identity function. This is our target. Okay, so we begin with the associative property of function, this and this, taking bracket in the first one and the last one, like this bracket, and here this is the bracket. Okay, so go through, this is remaining same, but it is identity function written here. This is this one and this one is equal to identity function, so iy, and f is here, and so this f double inverse and identity function composition is the function itself, and x is here, it is identity, and f composition is the function itself. And so these images of x under f double inverse and f are equal, therefore the function itself are equal, so this is equal to this. So we proved the theorem like this, and this is the end of the video. In the next video I am coming with the problems of the chapter inverse function and composition of functions. Okay, so I will also discuss some higher level problems in the next video. So till then, thank you very much. Goodbye.